Okay, why don't we go ahead and get started? So since we're having class on Halloween, I tried to wear the orangest shirt I could find, and we'll have a little bit of fun with it in today's lecture. I don't see any costumes, really. Oh, there we go. All right. Excellent. Okay, so today we're going to talk about dynamic memory allocation. It's going to be the first of two lectures that I think you'll find very helpful when you start the Malloc lab, which is the next lab coming out. So dynamic memory allocation is the way that from a program, application level program, you acquire virtual memory at runtime. And this is typically done for data structures for which you don't know the size until runtime. And the memory, so where's getting this memory from? It's getting this memory from the heap. So if you remember this picture that we've shown many times in this class, in various forms of it, this is the entire virtual address space. And we have the read-only segments and the read-write segments and so forth. And here's the heap, right? It starts from here, it runs up, okay, and it's delimited by this pointer, system pointer, the BRK pointer. And just to keep things in perspective, right up here is the kernel memory. Okay, that's outside of the purview of user code. And here's the stack that you've had so much fun with in this course, and the stack pointer. So the stack is growing this direction. There's also space for memory map shared libraries that grow up. But here's the heap here. And that's what we're talking about. Memory that gets allocated in this space right here. Okay? And of course, these aren't drawn to scale, right? I mean, typically these read-only and read-write segments are tiny, and the stack is generally not all that big, and the heap can be huge, depending on what you're doing in your program. Okay, so inside this heap, the dynamic memory allocator maintains a collection of blocks that can be of variable size, and each of these blocks at any point in time are either allocated or free. And so in this class, since we're dealing with C, we're going to talk about explicit allocators, which means that under the user's program control, you both allocate memory and you free memory when you're done. Okay, so for instance, malloc and free in C. But that can be contrasted with languages such as Java, which the user doesn't do the deallocation. So they do the allocation in the program by saying new, for instance, invoking a constructor. But there's no freeing in such programs. There's a garbage collector that runs behind the scenes and tries to coalesce the useful data and create free data, unused memory that it can then free up for later use. Okay, so that it's all done for you in those cases. But in this class, we're going to, and in your malloc assignment, we're going to focus on explicit allocators. Okay, so probably most familiar with malloc. Comes in the standard library. It takes a size and it returns a pointer. Okay, if all goes well, that's a pointer to a memory block that's available to the program, that's at least of the requested size, and there's certain alignment conventions on the x86-64. The blocks, the pointer points to something that's 16-byte aligned. Okay. A special case, if you happen to put the size to 0, this is going to return null. It's perfectly okay in that case. But the other time it's going to return null is if there's some problem, right? If it is unable to allocate the requested block of memory. So it's a good idea in your programs, if you call malloc, to see what the return is. And if it's null and you didn't set size equals 0, so it's kind of a surprise to you, then you're going to have to deal with that in your sort of error handling code in your program. Okay, it also sets this error number to this special value by Unix convention. But typically people don't pay attention to that. And then the flip side is, of course, you have the free function. You give it a pointer. Notice you don't give it a size, right? You just give it a pointer, and it basically says, I'm done with that piece of memory. And for correctness, that pointer better point to something that was either malloc or realloc. Okay, and realloc is maybe something you haven't used very much, if at all. That's if you've malloced a region and now you decide you want a larger region, or maybe a smaller region, and so you call realloc with the same pointer as before. One that you may be familiar with is calloc, which is like malloc, except well, there's one nice thing is that it initializes the allocated blocks to all zeros. Also, you have to the argument has to be expressed in sort of bytes. You have to give it the product of the size of the thing and the number of things. There's also this sbreak function that's moves that pointer I told you about, the BRK pointer, and it's used internally. Basically, the system will try to will allocate you some amount of heap space to start with, and then we'll try to keep all your allocations within that space, and only if it's forced to will it try to grow the heap further. Okay, using this command. So that's usually invisible to you unless you especially decide to use it. So here's a simple example, right? We've malloced something here, right? That's a particular size, and again, we check for the null. If it's null, then we know we have this error. Okay, and we're going to exit. Otherwise, since we called malloc, it was initialized for us. And in this program, evidently we didn't want them to be all zeros, so we initialize each p I to I. Okay, and so now our array p is all initialized and ready to go, and well, we free it. Okay, so not clear why this program made any sense, but presumably in a normal program, you would actually do something with p before you decided to free it. Okay, so when we talk about dynamic memory allocators in this class, we're going to make the following assumptions. We're going to assume that memory is word address. We're not going to worry about fetching bytes. Just keep things simple. That the words are integer size. So if it's a whatever the size of the integer is, that's the word. So we're not going to pay too much attention to that. And the allocations are double word aligned, as they would be in the x86 64. So we'll have pictures like this. We have each of these little boxes is a word, right? That's a word's worth of thing. And we color code with green the ones that are allocated. So this is an allocated allocation of 4 words, and here's an allocation of 2 words, and so forth. Here's an allocation of 6 words, and the ones that aren't colored are still free. So we have a free block of 2 words, as shown there. And you can see that the allocations are all properly aligned, right? They have to be aligned, these 2 byte boundaries, right? So that's good. Okay. So let's continue with an example. So here we have, it starts off all free, and now we get this first call to malloc for 4 times the size of it. So just to keep the notation small, we're going to define this siz to be size of int. And so we see that it just takes the first 4, and the next one just takes the next 5. And so then the question is, where does this next one start? Do we just go ahead and take, right, these next 6? I heard a no. Why not? It's not properly aligned, right? So we have to go to the alignment boundary, so it starts here. Okay, and we have a little bit of wasted space here, right? Okay, so now if we go to free, P2, that means we want to free this, what's that, lavender. And so it looks like that. Okay, and now if we do a malloc of size 2, then for instance, we can put it there. Okay, but we had some choices, right? Maybe we could have put it here. It might have been a better fit. Right? But in this example, we put it here. Okay, any questions so far? Yes?
Does it just randomly pick, or does it like go to the most optimized space available?
We'll talk about that. That's coming up. Yes, good question. Okay, so here are the, if you're writing a dynamic memory allocator, as you may just happen to find yourself doing in a few days from now, here are the constraints you have to know about, all right, and also within real, running systems. That you have no control over the mallocs and frees that your request that you receive as an allocator, right? The program can do whatever it wants. Although if they try to free something that hasn't been malloc, that's an error. So you can, assume that the frees are to things that have been mallocked. So because you have no request, no control of the sequence, you can't control the number or size of the allocated blocks. The programmer doesn't want to be kept waiting for you to say, okay, here, can I have this block of memory? And you say, can you wait a few minutes? I want to see what other requests come in. No, you have to respond to them right away. Okay? So you can't reorder or buffer requests. That's in contrast to other things in the system, right? I mean, if you think about, say writing out to a disk, okay? Typically, no one's waiting for you to write out to that disk, and so you can actually reorder requests. If we talked about how the disks work, and so if you're spinning past a place on the disk, and you might as well write it, even if it's out of order. Okay, it doesn't matter. But here we don't have that luxury. Of course, we allocate only from free memory. We must satisfy the alignment requirements. We can manipulate and modify only free memory, and we can't move an allocated block once they're mallocked. Okay, so why is that? Why can't we move an allocated block? Yes.
Because of like pointer arithmetic, the program might actually get over that thing.
Exactly. Okay. In C, you may have done all sorts of things about that. Now, and the other thing is that the programmer has to be able to free this thing, right? And so it's got a pointer, and it needs to be able to free it. And if you moved it, then it wouldn't know where to free it. Okay. Good. Okay, so there are a couple key performance goal of these systems is throughput, and that is that if you're given some sort of sequence, how fast can you complete them? Number of completed requests per unit time. Okay, and so for instance, if you're able to do 5,000 malloc calls and 5,000 free calls in 10 seconds, that's 10,000 operations in 10 seconds, so that's a throughput of 1,000 operations per second. All right. So because of this measure of throughput, you want to have routines inside your allocator that are fast, right? You don't want to be doing things that are very complicated and slow. And the other goal is this peak memory utilization. And we'll get to that in a second here, but that should kind of strike you as a weird goal, right? Peak memory utilization. We don't usually want to reduce the amount of memory. This is like, oh, can we maximize the amount of memory? Right? It's sort of strange, but you'll see. Okay. Basically, the trick is it's peak memory utilization relative to where that breakpoint currently is set. Okay. So the way to calculate that is that if you think of every malloc of size p, we'll call that the payload. It has a payload of p bytes. All right. And then at any point in time in the sequence of requests of mallocs and frees, we can talk about the aggregate payload, which is just basically the sum of all the things that are still allocated. Okay, so I've had a series of requests. Some things have been freed, I don't count those, but the ones that are still allocated, I just sum up their payloads. Okay, and that's going to be this, and after k requests, I'm going to call that piece of k. And then I also have this current heap size, and that's based on where this BRK pointer currently sits. Okay, and typically, in most systems, that only increases. They don't tend to take away heap memory once they've given it to you. And so we can think about that as monotonically non-decreasing. You're giving some amount of heap, and it could stay in one place for a while, and then it grows and stay in another place and so forth. But the sort of the maximum heap size that you have seen thus far is the current heap size. Okay, another way of saying it. So with that in mind, then we can talk about what we really mean by this peak memory utilization, and that is if we look at the current amount of heap we have, which again we said is the maximum we've ever had since this sequence started, and we compare that to this running aggregate payload, which can grow and shrink as things are allocated, deallocated. So we take the max, that's why they said peak memory utilization, we take the max of all those PI and divide it by HK. Okay, and that's going to be your peak memory utilization after K plus 1 requests. Okay, and it's just K plus 1 because we started it at 0. All right. Okay, so you can see why that's actually a good number to have high, right? You don't want to have you want to make good use of the heap. The system wants to make good use of the heap that's been allocated for the process. Okay, any questions on that? Yes?
Does that mean minimum padding? So like, what's it? It's not very intuitive.
So yeah, so what contributes to waste utilization? We'll talk about that in a second, but it's mostly it's mostly padding. It's the overhead for the whatever data structures you're using. As we'll see, what happens is that we do the bookkeeping also on the heap itself. That enables us to find things and so forth. And then just fragmentation. Okay, which we'll get to in a second. Yes?
Oh, what does P of I refer to? Like, is that
P of I?
K is like the sum of the current payloads, but what's P of I?
Yeah, we've used K in two different ways here. So if we think of, oops, I was afraid of doing that. So generically, this is be safe. After request RI, you have an aggregate payload PI, and then that's the PI here. Okay. So yeah, we should have used a different letter. We used K up there. Good. Okay, so poor memory utilization is caused by two types of fragmentation, internal and external. Okay, let's talk about internal first. All right, so we've set aside this block for the user, and somewhere in that block is the payload, which is the stuff it can actually use. But as we'll see, there could be some wasted space before the block, and we'll touch on that in a minute, and wasted space after the block for things like padding. Okay. But there's other things like was mentioned before about how much do we search for a really good fit for the block size requested. If we don't search for very well, and so we decide to, we find, like, for instance, we'll talk about something called first fit, which is you just march along, and the first time you find available free space that's bigger than what you've requested, so the thing fits, then you go ahead and satisfy it. You go ahead and use that space, all right? But that could create, a lot of sort of extra padding there, beyond just alignment padding. Okay, but the good news about trying to calculate how much internal fragmentation you have, it's a function of the requests so far, right? You can, if you run up to a certain step, you can look and do that calculation and figure out exactly how much internal fragmentation has shown up so far. All right, so let's talk about the other type of fragmentation, which we call external fragmentation. And remember our example from before. We've allocated this 4, we've allocated this 5, we've allocated this 6. It needed to be aligned. We freed the 2, okay? And so this is kind of the state of our memory. And now a malloc wanting 7 words comes along. Okay? And so from an allocator's perspective, this is like a yikes moment, right? That basically there really is, right, as it says at the top there, actually, there is enough aggregate memory, right? There's that 6 free things over there and the 2 there. So we had room for 7 if we had made some different decisions before. Okay, but based on the decisions we made up till now and the fact we can't actually move the allocated stuff, we can't coalesce them or anything, we're kind of stuck. All right? And the amount of external fragmentation you end up with is a lot harder to figure out, because it's sort of predictive. You have to know what's coming, right? I mean, the reason this and this were external fragmentation after this first step only arose because you had something come in that didn't fit, all right? I mean, if the next request had been 6 and the next request had been 2, there had been no external fragmentation and we would have been happy. So it depends on what happens in the future. Okay. Any questions on that? Okay, so I've glossed over a bunch of issues that you have to deal with if you're going to write one of these things. All right. The free command, as I mentioned, just gives you a pointer. It doesn't say free something that starts here and runs this long. Okay. So from your allocator's perspective, all you're given is this pointer. It says free this amount is free what this pointed to. Well, in order to know the extent of which to free, right? Because maybe you have right, so if I say free this guy here, all right, well, I've got allocated stuff all the way to here, but I need to know this, as an allocator that, I just mean to free up to here. This stuff still stays. Okay, so we have to talk about that. How do I keep track of these free blocks? Okay, they're scattered, as we've seen, throughout our heap. And I want to be able to find them quickly and so forth. There's this issue if I happen to choose a smaller block, if I choose a bigger block than what I need, how do I handle this extra space? Because it's still space, so maybe I can use it later, right? Then the earlier question, how do I pick which to use? There's multiple choices, and how do we reinsert free blocks? So if we free something, can we coalesce it with other things that are nearby that also been freed? Okay, so we're going to deal with those one at a time. So the first question is knowing how much to free. I'm just giving this pointer, right? How much do I free? All right, and the trick here, as is shown here, is that we're going to, so this is the payload, the block that I've given the programmer, and here's the pointer I returned, okay? So from the programmer's perspective, nothing's changed. From my allocator's perspective, I've stolen this block right here, this word right here, from the previous, from sort of this free stuff. So in this case, the dark is the gray is the freed. I've stolen this guy here. The gray is still the allocated. I've stolen this guy here, which wasn't being used, to put in a length field, okay? And so what this is saying is that this block size is my payload plus the space for this guy, which is 5, all right? And then if I later free that, then both this length field and this allocated thing are now available again. All right, so you can see that I'm back to this exact same state as before. All right. Okay, so any questions on that? Okay, good. So that tells me exactly how much to free when I get this one of these pointers. Okay, so now about the question of keeping track of these free blocks. All right, there's a number of different methods. In this class, we're going to focus on what's called the implicit list method. And basically what that is that now that I have these lengths associated with each allocated block, and I can do lengths associated with each unallocated block, unallocated segment of memory. And then, I can just follow them. So I start here, and it says 4, so I jump to here. I know that's the start of the next thing. It says 6, so I jump 1, 2, 3, 4, 5, 6 to here, and so forth. Okay? So now I'm able to get to the start, or in particular the length field of all the blocks, whether allocated or free. Okay. So the only twist that I need now from what I talked about before, once I've added these length fields, as I talked about before, is that when I get to one of these length fields, I need to know whether I'm dealing with a region that's allocated or not. Okay, I need to know the difference between this guy who's allocated and this guy who's not. Okay, so we'll talk about that in the rest of the lecture. But before we do, I want to give you the big picture, which is that there are other ways of doing free lists besides implicit free lists. And in fact, in the first part of your malloc lab, you're going to start off by doing an explicit list. So explicit list avoids a lot of the complications by just actually having a pointer. Okay, so if I have a free block here, all right, it has a length field as I mentioned, and then it also has right here a pointer that skips over all the allocated ones and gets you directly to the next free one, right here. Okay. So that's nice because you don't spend a lot of time sort of bouncing through, the ones that are already allocated, right? You can imagine as this space gets more and more filled up, you might spend a lot of time in this top method hopping through ones that you've already allocated. Okay. Where this one jumps immediately to the next free thing, and the only issue is it big enough or not for what you're trying to allocate? Okay, but what's the drawback of this compared to the free? Yeah.
If you allocate a piece of memory that's free, then you have to go to the previous free memory and adjust the pointer to be the next free piece of memory.
Right. Yeah. Yeah. So that's right. So if, for instance, you allocate this piece here, then you need this pointer to point here, right? Okay. And you notice in this structure, I didn't give you any back pointers, okay, to go backwards. So basically that means as you're marching along, you're going to have to keep track of not just where you are, but the one before, so that you can you have this pointer available to change. Okay. And the other thing is that you need space for these pointers. Okay, to add space, right? And these, yeah. Okay, and that could be like 64 bits. Okay. Another method that we'll cover in the next lecture as well, that you're going to want to consider as well for your malloc lab, is having different classes of free lists based on size. Okay, so maybe you have like a free list for all the blocks that are size 4. Okay, where the available space is size 4, and maybe you have ones of all the ones that are size 8 or 16 or whatever. So some different combinations and you have separate free lists. So therefore you don't waste your time hopping through ones that clearly aren't going to be the right size. Okay. The extreme of this would be if you had sort of you kept all the available blocks sorted by size, right? Say in a balanced tree that allowed you to search. So you'd come in with your key would be the size you're interested in, and you'd search through this balanced tree using that length as a key, and then you'd find the one that was the tightest fit, for instance, to what you're doing. Okay, so that would get you without the say overheads of segregated free lists. That would get you the sort of the tightest fit to what you were looking for, but then there's all the overheads of search trees and so forth. Okay, but today again we're just focused on method 1. Okay. Good. So I mentioned that in addition to size, the thing about the implicit free list is that, and let me just remind you again, right? So we've got implicit free lists. We've got these length fields that we use implicitly, and we said we needed to tag as either allocated or free. Okay, good. So what we're going to put this tag of allocated or free. Okay, we don't want to have to store this information in its own word. Any clever tricks? Yes. The block, the lengths of these things are all unsigned, so we're already using that bit potentially for. But you're on the right track. You're just wrong end of the bit pattern. So what's at the other end of the bit pattern? Yeah, the least significant bit. And so why is that available? Because of alignment, right? That basically when the blocks are aligned, then some order address bits are always 0. And so you treat them as being 0, and you use the fact that they're 0 to squirrel away a bit, say 0 for free and 1 for allocated, in that space. Okay. All right. So what that means is that you don't, this word that you used for the size is good enough because you just use this last bit. But when you read the size inside your allocator, you want to mask out this bit. You want to basically view it as always set to 0. And if you're interested in what this bit is, then you want to sort of mask only this bit. Right? You want to just retrieve that bit. Okay? And we'll see examples of that in a second. Any questions on that? Yeah.
Why are the lower address bits always 0?
Because things are aligned, right?
How does that make it always 0?
Okay, so this, yeah, so the size, so for instance, the size is, I mean, so yeah, I see the confusion. Okay, so in this lecture, we've sort of said everything is in word sizes and all the lengths are in word sizes and things like that, right? But,
Oh, because it's 2 word alignment and then you have 1 extra word.
Okay, that's good. Yeah, you answered your own question. So basically what happens here is that even if you wanted all these length, all these size fields, sorry, are, they're one less than the alignment boundary, right? So alignment boundary is here, here, and here. Okay. So so you know that, and these sizes include the padding, right? They jump you to the next length field. So you know that these things are always, as you said, a multiple of 2. Okay, so that last bit will be 0. Good. Good question. All right. Okay, so in this diagram, what we've done here is we've labeled them as sizing words and allocated bytes. So this is 2 words and unallocated, 4 words and allocated and so forth. Okay, and we're showing the double word aligned boundaries. And then as a result of that, there's always, because we have to have room for the header for the first guy, there's always going to be this first unused word. That's all right. And there also have this notion of what's called an end block, which is at the end of this list. And it turns out that the most convenient convention for that block is to say it's a size 0 and it's allocated. Okay, and it's kind of arbitrary to call that thing allocated because it's not really allocated, but it turns out that when we look at coalescing later, you don't want to coalesce past this thing. So you, by setting this to 1, things are, you won't try to coalesce with it, right? You'll stop, and that's good because you don't want to, coalesce to something that's really not there and it's off the end. All right, so that'll become clearer later when we talk about coalescing. But I just wanted to highlight that because it looks a little strange on the slide to call that thing allocated. All right. Okay, what about the question of finding a free block? All right. So first fit says you search from the beginning and you choose the first one that fits. Okay. And so here's the simple little code for that. Right. So you you do from the start. Right. So right here, start. While it's not past the end. Okay. Again, the end would be delimited by that end block. But in your code, you probably have these as some absolute starting and ending addresses. Okay, what am I going to do? If I'm not past the end, then what do I want to do? If I take what that pointer points to, and I and it with 1, what does that do? Yep, just extracts that bit, okay? So if that bit is 1, this is no good to me, okay? But if the bit is 0, that's free, all right? So then I go to check to see if it fits, right? And so if the length field is, if it's less than or equal to the length I'm searching for, then it's too small. And so I continue this while loop, okay, by going to the next block. Okay. So notice I have to do, in order to jump to the next one, I have to take that size field and I have to AND it with -2 to get rid of the zero out the allocated bit. Okay, so that gets you the real size, and then add that and continue. Okay. All right. So any questions on that? So the only thing that's sort of a little bit subtle is why this is less than or equal to, right? Because you'd think if it's equal, that means there's enough room. But the length field, if you recall, like this is a length field of 4. It includes the length for this guy here, right? Because he says hop 4, 1, 2, 3, 4. So there's really, if the length field is 4, the size field is 4 here, there's only space for 3. Okay, so that's the only reason the code says less than or equal to as opposed to maybe more intuitive, less than. Okay, so the good news is that with first fit, it's you're done as soon as you find something that fits. But the bad news is that it may not be a very good fit, and things tend to splinter at the beginning of the list because the little things sort of clog things up. So in order to get around this fact that all the sort of clutter is occurring at the beginning of the list, there's this thing called next fit, which is the same as first fit, but instead of always resetting when you want to find a place for something at the beginning, it just continues where you last left off. Okay, and this is really good. For instance, if the thing that you want to find is at least as large or equally as large as the thing you just looked for, right? Because if you just search, and you weren't able to find, and this was the first place you could find a space that was big enough, then there's no reason to go search again if there hasn't been any frees in the meantime, right? Because you're going to fail if that new thing you want is the same size or larger. So the next fit says, oh, well, start here and look forward because I know everything behind this place spot didn't work out. So often faster because it avoids rescanning unhelpful blocks, but some research suggests that fragmentation is actually worse. All right. So the other extreme is best fit, where you in some sense go through all the possible choices and find the one that has the fewest bytes left over. Okay, fits with the fewest bytes left over. All right. So this has the advantage that you're actively working to avoid fragmentation, and so it usually improves memory utilization. But it's typically slower because you're not just stopping the first time you find something that works. You're like searching until you find something that that's the best you could hope for, right? And maybe, for instance, if the best you could hope for doesn't exist, right? If everything is bigger than what you want by too much, you have to go all the way to the end before you discover that and say, oh, okay, I guess there really was nothing that was the exact size of 1 or the exact size plus 1. So now I've just wasted my time running through the whole thing. All right, yes?
So whenever you malloc a type, like an int, you also have to malloc an extra word that keeps track of the size of the type?
So yeah, behind the scenes, unknown to the programmer, you're also counting for that length field.
But that extra field doesn't affect the padding, right? Because like in the padding questions, we didn't have to know about that extra word actually being there. Because like, if your int is like four words, and then like you have an extra word, so it's actually secretly 5 words, that doesn't like affect the padding, right? Like it's really
So you need this to be, like for instance, you needed this to be, these are good questions. You need this to be double word aligned, right? Okay. So, so this allocation here was actually an allocation for 2. Okay, size. The thing that was requested was size 2. All right. So in that case, we had to pad by 1. Okay. But notice size 3 would have worked, right? We wouldn't have had to do. I mean, the quote unquote padding would have been this guy here, but right. But notice that a size 4 doesn't even fit if I did a style of allocation. Okay. So yeah, so I guess you're pointing out that technically, when we ask these padding questions and exams and the padding question we had earlier, we're making some assumption that we're not losing any space on the heap for these kinds of size fields and stuff like that. Just because we hadn't covered that topic yet, you know. But yeah, that's a really good question. Okay. Okay. So there's a notion of splitting. All right. So let's suppose we're coming along. We're trying to find something size 4, and remember that 4 actually only fits 3, so this isn't big enough. Sorry, this isn't big enough. But we come here and we see a 6, and we say, okay, that can hold up to things of size 5, so it certainly can hold this 4. Yeah, this is a little confusing actually. So basically this can hold, what we're holding here is these 3, okay? And then we're gonna have this leftover space, right? And this leftover space, so you had 6 here before, and now we're allocating something of size either 2 plus padding or 3. And we have to have we have this length field, the size field as well. And so we basically use up 4 out of the 6, okay? And so now what we do is we just figure out what the remaining part is, and we subtract basically 6 minus 4, and we get 2. And so that's what this code is doing, all right? This is going through, this is a routine within your allocator, right? That says I'm going to allocate something that needs a length 4, including the size field. And so you say, well, the new size is the, needs to be rounded up to even. So you add, this is a way of rounding up to even. If you remember your bit tricks from lab 1, right? You're going to right shift and then left shift. That's a way of zeroing out that last bit. Then you're going to mask out the low order bit, okay, on the old size. All right, because right, there could be a 0, 1 there. And then we want to set the new length, which is, we want to indicate this is now allocated, so we put or that new size with the 1, okay? And then if new size was less than old size, okay, as opposed to equal to old size, then we know we have something left over. all right, and we just figure out how much that is. So we take the old size, which was 6, minus the new size, which was 4, and we just have to figure out where to store that, okay? And where do we store that? Well, this is the P, again, this is not the P that we return to the user, this is the P in our sort of walking through the free list P, right? This is internal to our allocator. And we say, well, the new P is going to be P plus the new size, okay? So that'll be placed here, okay? So whatever the P was plus whatever the new size took up places it here. So we place a 2 in that position here. Questions on that? Okay. What about the opposite, freeing a block? Okay. So one approach is that the only thing you do is you just clear the allocated bit, right? So if you take the thing that's stored, you take the thing that's stored here. This is really 4/1 because it's allocated, right? And you just want to convert that to 4/0, and you do that through this bit manipulation that just zeroes out the last bit. Okay? So that's fine and good. That would be enough. But then, what if you get now a malloc size 5? Okay? And the way you set this up is you only see, 4, 4, and 2, and so forth, right? So this is, again, another one of our yikes moments, right? And, the allocator doesn't find it necessarily, right? So that's why we want to do something. So we have a couple of choices. One is, as we're marching along, we can, as we've freed this space, instead of just sitting this byte, we can actually march along and look at this pointer and say, oh, does this also have a 0? This also has a 0 in the allocated bit. Then it's also not allocated. So I can go ahead and collapse this and return this to a 6. Okay? Okay, and that's what this is showing here. That basically this is logically gone by just, once you've done this zeroing out of the allocated bit here, you find where it pointed to, which is here, and you say, well, if I just yank out the allocated bit and 0, which means unallocated, then I'm going to actually just jump over to here by 6, 4 plus 2, whatever's there. Okay? And now that's logically gone, and you're back to where you were before. All right? Does that make sense? Okay. Anybody see a problem with this? Yes?
Something for the previous block is going to mean you need to traverse the list again because you don't have a pointer to it.
Exactly. Exactly. So this was the case where the thing you were trying to coalesce with was ahead of you. But suppose we had a reverse situation where 2 was the one that was, this was the one that was allocated, and this one was not. And now my forward pointer doesn't help me at all. I want to coalesce backwards. Okay? Good. All right, so fortunately there's a solution for that. A number of solutions. The first one proposed by Donald Knuth called boundary tags. And that is simply that in addition to storing the length at the beginning, so it allows you to jump forward, you also store the length at the end, and that allows you to jump back. Okay? But of course the problem is that now you're storing the size in 2 different places, right? So that's wasting space. Okay, so it looks like this. Same thing, we've got the size and the allocated bit here, and the size and the allocated bit here. All right, and that allows us to go backwards and forwards and coalesce backwards and forwards. Okay, so if we consider each of the 4 cases, right, we're trying to free this block here, and the 4 cases are, it's surrounded by allocated stuff, the thing before it's allocated but not the thing after it, the converse, the thing before it is free but not the thing after it, and they're both free. Okay, so how would we handle all these cases? The first case is simple. Okay, we first free this by setting these bits to 0. And then we look before and we see, oh, that's allocated. We look after, we see that's allocated, and we're done. Okay, that was the easiest case. The second case, we're trying to free this, and the one after it is unallocated. Okay, and has some size M2. Then what are we going to do? We free this by setting this to 0 and this is 0, and then we look at this guy, okay, and we see it's also 0. So we jump by M2 to get to the M2 minus 1, I guess, to get to the end of this, and then we see what the end is, and we can write the new size, which is the sum of these n and M2, and an M2, and then keep that at 0. Okay, any questions on that case? All right, okay, so now this case is the case where we had to come up with boundary tags to solve. So this is the first interesting case, but it's pretty simple, right? So basically, we check here, we see it's allocated, so there's no reason to coalesce that way. We check back here, we see it's unallocated. We use this boundary tag to jump M1 and get here, and that enables us to update this to be the sum of those two sizes, and of course it's unallocated. And finally, this case where neither of them are allocated, we just do both directions, and we end up getting n plus m1 plus m2 and unallocated. Okay, questions on that? Yes?
Why can't we coalesce lazily and not coalesce unallocated?
So that's an option, right? You can defer coalescing till later if you want. This has the advantage of, I mean, in some sense, when someone's gone to free something, you've got potentially some time there. It's not on the critical path typically for anything, and so it's good to do some work ahead of time. If you do it immediately, then you're not coalescing on the. It's like if you didn't do this immediately, then the next time through you'd be hopping like this, and so you'd be doing these hops, and that would slow up the actual allocation. Okay, and then you have to, it'd be more complicated. You have to do this, keep track as you're going. And you're right, but after having marched through this, you could then create it to make it look like this. But that's just delaying the allocation, which is typically when there is something waiting, the program is waiting. So the more you can push computation time to the free and less to the actual time of allocation, the better. But fundamentally, there's nothing wrong with deferring coalescing. All right, with that, boom, quiz time. All right, let's see, many of you have done. Okay. If you want to use a region of memory to store different types, you should use a union. This is a reminder that will come in very useful in MATLAB, okay? Which is why we put this question here. Just to see how you're coming with Shell Lab. Well, maybe not so good. All right. Well, nice even distribution though. Okay. So who can tell me why this is an error in the first place? Somebody doesn't use the answer. How about you in the red? That's right. Okay. So you cannot set the handler for sigkill to be ignored. Okay. Now, maybe a little more subtle whether the compiler catches it or the runtime catches it, but it turns out that the compiler doesn't really have enough information to figure that out, and so this will get captured at runtime. Okay. So user code, you can't block sigkill, you can't ignore it, you can't do anything with that. Kernel code can, but not user code. All right, and the one that was related to today's lecture, good, you did pretty well on that. The answer's not showing up on here. I don't remember what it says. What was that on? Anyway, you got it. Most you got it right, whatever it said. Forgotten. Yeah, and so the boundary tags enable you to go backwards and forward. Minimize the internal fragmentation. It turns out that if you call internal fragmentation as sort of how much, a big part of that is how much your own data structures contribute to loss of available memory. And because you have these tags on both the front and the end, it's actually not very good in terms of internal fragmentation. So we can argue semantics of what it means to minimize, but it's not one of the better solutions for internal fragmentation. Okay. All right, and that's kind of. All right, and so the first clue is shown on the slide here. Which blocks? So we have both this header and footer sizes, but which blocks do we actually need? Do we actually care about the footer tag? Allocated ones or unallocated ones? So it turns out that it only comes up when you do coalescing, right? All right, so we'll show you a trick here. All right, so, okay, so boundary tags are needed only for the free blocks, okay, because they're used basically to allow you to do coalescing when you're freeing consecutive things. All right, so we mentioned that if sizes are even bound multiples of 2, then we had 1 spirit bit. When sizes are multiples of 4 or more, we have 2 spirit bits. Okay. So let's assume that. And again, this would come back to the case of if size was actually accounted for in bytes as opposed to in words, as it is in this lecture, then you would have multiples of 4 bytes clearly for sizes once you did it account for padding. So we're going to use that extra bit in a kind of an interesting way. We're going to set it to 1 if the previous bit is allocated and to 0 if the previous bit is free. Okay, so we're going to get rid of this altogether, and instead we're going to do some extra encoding in the header. Let's see how that works. Okay, so we have those 4 cases, remember. So the first case is that we're trying to free something where the thing before it and the thing after it are both allocated. All right. So initially, before we do any freeing, we see allocated, allocated, allocated. Okay. This is our cheat sheet, right? The current block allocated is the last bit the previous bit allocated is the bit before that. And we use those 2 bits because the address bits are always 0 due to alignment issues. Okay, so if we want the actual addresses and sizes of things, then we just 0 those out. Okay, so what do we see here? So we free this. Okay, so this is now unallocated. And now we look at this bit here, and this bit here was a 1. So that means that the previous block was allocated. Okay, and that's indeed what we show here because it's in green. And so we know we don't have to do any coalescing backwards. All right, and so we leave that as a 1. And then because of this n, right, we can jump to here. All right, and then we can look as before as to whether this is allocated or not. It turns out it is allocated. And so we don't have to do any coalescing there. So this remains a 1. And the only thing we have to change in this guy's header is the fact that now, from its perspective, its previous block is now unallocated. So it's gone from a 1 here. I don't know if you can still see that under all my chicken scratch. It's gone from a 1 here to a 0 because now I freed this and it's unallocated. Okay? So with just the... actually, this shouldn't be here. There we go. Just a mistake on the slide. All right, good. So from just the information of this extra bit, we knew we were able to handle this case and set this bit to maintain the invariant. All right. So what about our case 2, where it's the one after that's unallocated? Okay. Oh, I see. Never mind. Sorry. I see. So for I'm getting myself confused here. So for the ones that are free, we are going to go ahead and maintain both the header and footer. Okay, it's just these ones that are allocated, we don't want to waste space in the available allocated stuff for the footer. Okay, so this is the steady state, right? That basically for something that's unallocated, you've got both the header and a footer. And in this case, the previous block is allocated, so that's why it's a 1, and it's a 1 there. Now, after we free this, what's going to happen? So we'll use this n to hop to here, okay? And we'll see it's unallocated, all right? So that allows us to coalesce with this by adding this n plus 2. And so it ends up looking like this, okay? Okay? And from the perspective of this bigger block, its previous guy is allocated. Okay, so that's why that red bit stays 1. All right, so what about this case? So the question mark here means we don't really care. Whether it's 0 or 1 is not going to influence what's going to happen here. So what's going to happen here is that you're going to free this. Okay, so that's going to set this one to a 0. And now, it doesn't matter whether you do the previous or the next first. But let's say we do the previous first. So we see this 0 and we say, oh, this is unallocated stuff. So what that means is that the footer actually contains a length field. So I can just hop just this 1 back here, retrieve this M1, and then I know that I can add n plus M1. So sort of the intermediate step. This is going to intermediate step ends up looking like the n plus M1 and the 0 and n plus M1 here. 0. And this one we haven't touched yet. And so from that step then, we have this n. I guess I had to remember the n. So we have this n and we go here, and now we see that this is allocated, and so we're done. Okay? So it ends up looking like that. Okay? And the only thing, I forgot to mention this, the thing we have to do is make sure is we set that this goes from a 1, previous block allocated, to a 0. And otherwise, we kept it at 1. Yes?
I'm just curious about why we have the question mark for our previous blocks. If the block prior to it was free, wouldn't we have already coalesced them, so the block has to be allocated?
That's true. That's true. Good point. Okay. So in the final cases where they're both free, And so the end picture looks like this, and basically we do kind of what we did before. Let's say we first go n ahead. We get to this guy. He says m2, so now we can go to n plus m2. So we get to this guy, and we see that the previous is unallocated. So we go back. Right. So when we went forward, we looked at this bit. When we go back, we look at this bit. We see it's unallocated, so we go here. We know that this is actually a footer, and so now we can add M1, and so the end result is this and this. Okay, and it's unallocated. Questions on any of those 4 cases? Clear? Okay, we've talked about that there's a number of decisions to make in an allocator. One is the placement policy. Do you go for the first one that fits, the next fit, the best fit, and so forth? Each of these policies has a trade-off between lower throughput, meaning it takes you longer to find what you want to hand over to the user, but possibly saves you on fragmentation, which is a good thing. Interesting observation, one of the reasons that segregated free lists, remember these are the ones where you have different allocation classes for different sizes, is a somewhat popular thing to do, is because it actually can approximate a best fit placement policy without having to sort of do this lengthy search. Okay, and again in your malloc lab, particularly the second part of it, you're going to play around with a lot of different combinations of these things to try to optimize. Okay, it won't just be one or the other, it'll be this mix of different policies. So you can be able to think long and hard about what works. We talked about splitting policies. When do we go ahead and decide to split a free block? How much internal fragmentation we're willing to tolerate when we do that. And then we talked about coalescing policy, immediate coalescing, which was what I was presenting, which is coalesce each time a free is called. As was in the question, you could also defer coalescing to try to improve the performance of free. For instance, you can coalesce as you scan the free list for malloc. So as you're going forward, you can do the coalescing. Or you can coalesce when the amount of external fragmentation reaches some threshold. So there's different options there. But again, generally, I think malloc is more on the critical path than free. So you tend to want to do it immediately. All right, so to summarize this lecture, we talked about implicit free lists. The advantage is that, believe it or not, I know it may have sounded complicated in the lecture, but conceptually it's actually very simple to do these implicit lists. Drawback is that the allocation costs are linear time in the worst case because you're marching through these linear lists. The good news is you can free in constant time even with the coalescing. Memory usage depends on which placement policy you decide to use. Although they're not used in practice because of this first problem, the reason we spent a whole lecture on them is because they're a good way to introduce the concepts of splitting and boundary tag coalescing and so forth that you actually end up using in all the different kinds of allocators. And you will need to understand for your malloc lab. Okay, happy Halloween.